This is level 2 of the CFA program, the topic on quantitative methods and the learning module on model misspecification. You might be tempted to think of misspecification in terms of models that are, let's just say, nonsensical. Suppose you're a Tiger Woods fan and you want to investigate the length of his drives off of par fives during major golf tournaments. And to do that, you collect some data on independent variables. Let's suppose one of those independent variables is the number of times that Jim cuts his grass during the summer, and another one is the number of times that Jim shovels his driveway during a snowstorm during the winter. Well, that's a nonsensical model. Of course, it's going to be misspecified, but the limits of misspecification are not just confined to nonsensical models. And so let's go ahead and talk initially about what are the requirements for properly specified models. I mean, first of all, they need to be grounded in fundamentals of finance and economics. All the stuff that we're learning in the CFA program, you have some kind of obvious relationships. I mean, for example, there's an obvious relationship between the value of the US dollar and the rate of inflation in the US economy. That sounds like a sensical relationship. The model also has to follow the regression assumptions. You know, one of them is linearity. Of course, we expect the relationship between the independent variables and the dependent variable to be linear in nature. We also want the model to be in its simplest and most skeletal form possible, right? We don't want a model that looks like this. Can you see my hands going way out? We want a model like this will be sufficient. We also need a model that performs well out of sample. You know, suppose you're a gardener and in your backyard you have, let's say 10 different rose bushes. And you water each one differently, and you put different fertilizer in each one's bed, and you use different soil mixes in each one, and you want to determine, what is the best way to grow beautiful flowers and beautiful roses. Well, you may come up with a model, and that model may work really well, but it has to work if your neighbor did the same thing, right? An out of sample forecast. If your neighbor did the same kind of thing. Of course, you have neighbors you're kind of competing against each other, so maybe that's not a great example. But the model also has to be robust. In other words, if everybody in your neighborhood did the same thing that you did, their models would be identical. And then finally, it has to be in the appropriate functional form. Go back to my Tiger Woods example. Is there a linear relationship between number of times I cut the grass with my John Deere tractor and the length of the drives of Tiger's par fives? Who knows what that relationship might be? It's probably non-existent, but there might be something in there that you could uncover. Instead of a line, maybe it looks like this. Maybe it looks like that, or maybe it looks like that. Who knows? So anyway, remember those 5 elements that are required for properly specified models as we get to the learning outcome statements about misspecification. So we'll start with just some general ideas, and then we'll talk about homo and heteroscedasticity, and then correlation and multicollinearity. All right, how about categories of model misspecification? So what was our first category? Jim's first category, nonsensical, right? But what happens is that we can go through all of those 5 elements that I described, and we can still have a model that is misspecified, even if it has proper financial relationships, even if it's skeletal, even if it performs well in out of sample forecasts. So categories of model misspecification, different functional form. All right, so what does that mean? That means that, if you have a model that's this big, boy, maybe a model that's a little bit bigger is better. Maybe it adds 1 or 2 independent variables. So look at that first one here, omission of important variables. You can also use incorrect form of the data. Remember in level 1, we had some conversations about transforming data. And by the way, we're going to have great conversations in, I believe it's module 5, when we do some time series inside of this topic. But sometimes relationships are not strictly linear, so we can transform those independent variables into simple linearity. Pooling of incorrect data. Remember in that most recent module, I was telling you about the R-squared with the Fama and French model in terms of trying to figure out what is important independent variables in describing stock returns. Well, they used portfolio data on the left-hand side of the equal sign, so they pooled the data and they did it correctly. Of course, they did it correctly. But sometimes you can pool data incorrectly. I mean, you could add, let's go back to my silly example, you could add the number of times I cut the grass to the number of times I plow my driveway. You could add those together, and then you could multiply by 8, and you could do something else to it, and that probably wouldn't make any sense at all. Now, what we need to do is we need to make sure that we're aware of what kind of data set that we have. Do we have cross-sectional data in which we're taking, let's say, a sample of dividend-paying firms? Suppose we have 100 of those dividend-paying firms, and we use that as our dependent variable. Let's call it, maybe dividend yields. And then over on the right-hand side of the equal sign, we select some independent variables like, maybe changes in operating cash flow and quality of the executives, et cetera, et cetera. So that cross-sectionality, what that does is that eliminates a lot of these misspecifications. But if we have time series data, and I just referred to, I think it's module 5, we're going to have a great conversation on time series where we'll talk about unit roots and first differencing and all sorts of fun stuff. But in this module, the Institute really is giving us, kind of a parsimonious or skeletal idea about this misspecification. But clearly what can happen here during time series is that you can have a relationship between how many times Jim cuts the grass this month versus how many times Jim cuts the grass next month. And so notice that first diamond point. When independent variables are correlated with the residuals in a time series model. So when you read in a vignette about time series, it should percolate in your brain, okay, I'm going to have some problems with serial correlation. Now, this can occur because you can use lagged dependent variables. You can use a function of the dependent variable. I mean, let's go ahead back to my Tiger Woods example. Let's suppose we take the natural log of the distance off the tee as one of the independent variables used to describe the dependent variable of the number of yards. All right, so notice that embedded diamond point there. This is analogous to forecasting the past. That's why we've put those Back to the Future references there over on the right-hand side. Those of you who've watched my videos over the years note that I talk about Jaws, I talk about James Bond, and I talk about Back to the Future pretty regularly. But every example that I give, has something relevant to the exam. And then independent variables measured with an error. Of course, what we're going to do is we try to come up with this best independent variable. And so maybe we pick spot rates and we should have used forward rates, or maybe we used the par yield curve instead of the forward yield curve. So there are easy ways to make these mistakes. And then, of course, remember, we always assume some kind of stationarity among and between and describing the data over time. We want data to look like this, which means we want stationarity in means and standard deviations. So that's that thing there. I mean, if they go like this, then the model's probably misspecified, and we have a greater chance of that happening in time series data. All right, so here's a great exam question. What are the effects of model misspecification? Here, let me go ahead and just give you Jim's interpretation. Yes, the results stink, and the model stinks. and you really can't do anything with it other than take it and throw it over there into the garbage can. So biased regression coefficients, inconsistent regression coefficients. Then you have unreliable test results. And then, of course, the consequence of those first two diamond points is that we're going to have inaccurate predictions. I think in the last module, one of those, the final LOS was to go ahead and make a prediction. And remember, we had inflation and we had real interest rates, and we were trying to predict the value of the US dollar index. And so we came up with some number, but if our model is misspecified, then boy, that really doesn't make any sense. That's exactly like trying to predict Tiger Woods' drive off the 13th tee at Augusta National Golf Course by inputting, hey, Jim cut his grass 17 times last summer and he plowed his driveway 4 times with his snowblower. All right, how about this idea of homoscedasticity, which, look on the left graph there. Here is the relationship between the error terms and the relationship between the x and the y variables. So look at that. Those error terms, they're pretty much consistently surrounding the linear relationship, right? So what do we know? We know that whenever we perform any kind of a statistical analysis, we're going to do it with an error. But what we want to understand and know is that our errors are consistent, and that's what homoscedasticity means. And look at all of those individual values there. Now remember, those are the residuals there. So what are we saying? That they're probably pretty close to the blue line. But then what happens? Look over on the right-hand side. If we have heteroscedasticity, we have the variance of those residual terms moving outward like that, which clearly is a violation of our homoscedastic assumption. What this does is it makes f-tests unreliable. Now, the good news for all of us who want to perform this research is that there are 2 types of heteroscedasticity. So let me go back here. So we can have heteroscedasticity that is okay. We can have heteroscedasticity that is not okay. So unconditional heteroscedasticity is perfectly fine. It almost never causes major problems. And that's because if we truly have unconditional heteroscedasticity, it occurs randomly. And that randomness, then, you have the increases then are offsetting the decreases, and so they kind of cancel each other out. I mean, don't ever tell your stats professor that I said that to you, but that's probably a good way of thinking about it. So look at that first arrow point. When heteroscedasticity is not correlated with the values of the independent variables. So this is kind of consistent with one of those assumptions. If we have conditional heteroscedasticity, well, then this just throws everything right out. Look at that second arrow point. Cannot use regression for statistical inference. Now, the good news for us practically is that when we're performing this research using software, there will be tests embedded in the output that gives us a measure of heteroscedasticity, and then it will tell us how to correct it, and then it will correct it for us, and then it will give us new output. But that's probably not going to happen on the exam. What the Institute is likely to do is give you the BP chi-square test. So look at that picture down on the bottom right. So remember that chi-square distribution is not a normal distribution, right? And so what we're concerned about is just the one tail, that upper tail. So what we're going to do here is we are going to use all of the interesting conversations we had in that previous model about R square, and we're going to use that R square to actually compute the Breusch-Pagan test statistic. Now, let me caution you. Look in the very middle of the slide. There's the test statistic. We just take n, which is number of observations, times R square. Now, this is not the R square from the regression model. Look up at that first teardrop point. It's a regression of the squared residuals from the regression equation on the independent variables. All right, so this test is different from the R square that is the natural output when you use all those software packages. So we're going to take n times that new r squared. Think of it as the BP r squared. So let's go back to that example that we used in the last module. There's our US dollar index as the dependent variable. Rates of inflation, rates of real interest are the independent variables. And so notice the second circle point. The squared residuals from the original regression on the independent variables, that new r squared is around, well, let me just round up to 20%. And let me remind you, those of you who watched that recording on that last module, what did we have? We had an r square of about, let me just remember, what was about 68 or 70%, and then we adjusted it. I think we computed that on one of those slides. We computed it and it was 58 or 59 or 60%. So I promise you that the Institute is going to say, here's the r square. What did I say? It's around 60%. And then somewhere else they'll say, hey, here's this BP r squared, and they'll say it's about 20%. And they'll say, go ahead, test for the presence of heteroscedasticity. So make sure you take the 10, and n was 10 back in that example, and then make sure you multiply it by the correct r squared, the 1874, not the 60% or not the 68% or whatever those numbers were, right? So then we need to compare that. Here, let me go back to this graph here. So we need to look at that far right side, right? This is a one-tailed test. So we just computed our test statistic, what was that, around 2. So we need to compare that to what's known as the critical value. So let's go ahead and get out our table. And remember, if the Institute wants you to look this number up on the table, they're not going to give you the entire chi-square distribution or the F distribution or T or Z. They'll just give you kind of parts of it, so they can fit it into a vignette. So at the 5% significance level, so let's run our finger all the way over to 5, and let me just remind you that at 95%, right, that entire confidence level is over on the right-hand tail. This is a one-tailed test. So we have 5%, and then we're going to come down degrees of freedom, which in the chi-square distribution is K, right, number of independent variables. What were they? Inflation and real interest rates. So that's 2. So you go over and you get, what is that, about 6, right? So what are we saying? We're saying, hey, we are failing to reject the null hypothesis that we do not have conditional heteroscedasticity. All right, let's move back to time series. We're concerned, as I said previously, that the independent variables are related to each other, right? I mean, the number of times that I cut my grass this month is probably related to the number of times I cut my grass last month, because during the summer, it's hot out and it's sunny out, and so my grass grows, and so there's probably a relationship between my June cutting and my July cutting, and my November cutting, which is 0, and my December cutting, which is, actually I did cut my grass in the beginning of November. So November cutting is 1, December cutting is 0, January cutting is 0, February cutting is 0. So those are probably related. So we need to concern ourselves about positive or negative serial correlation. So look at the positive one there. That looks an awful lot like your graph on the business cycle, right? So, the reversion to the mean, so to speak, looks like an up and down motion. So positive autocorrelation. Negative autocorrelation is just the opposite, where you have changes in the sign from one sign to the other. Here's a great possible exams. So effects of serial correlation, incorrect computation of standard errors, which leads to impossible predictions or inferences. All right, so here's the great exam question. Look at positive serial correlation. Excuse me, standard errors are underestimated. So think about the denominator. Instead of being this big, the denominator is this big. So they go into the numerator more times. So the t-stats are inflated. which means there's an increase in the probability of a type 1 error. Negative serial correlation, let me just go back. Of course, that's the opposite, right? So standard errors are overstated, which means that the F statistics are understated, and T statistics as well. So the type 2 error increases. Now, we'll do some really intricate details about Durbin-Watson in that Module 5. But for now, what we're going to do is use the Durbin-Watson test, the DW test, which can be approximated right there in that third bullet point, 2 times 1 minus some kind of a correlation coefficient. Now, we need to make sure that you're aware that that correlation is between the residuals from the regression from one period to the next period or previous periods. And so think about my number of times I cut my grass. We're doing the residuals in January and the residuals in February, which are going to be 0 because there's no cutting of the grass. But of course, they're probably going to be related from June to July and then July to August. So this module doesn't go into too many details here, but just remember in the very bottom, positive serial correlation, that DW statistic will be less than 2, negative serial correlation, that DW statistic will be greater than 2. And just pause and take a deep breath, because when we get through Module 5, you'll know everything about Breusch-Pagan and Durbin-Watson. And then lastly, let's go ahead and have just a brief conversation on multicollinearity. It was one of those assumptions that we talked about, not only in this module in the beginning, but also in the last one, and even the first one in this section, that the independent variables are in fact independent, which means they don't have any correlation. What happens if they are highly correlated? Well, then slope coefficients are unreliable. You can't really tell what's going on between and among the independent variables and the dependent variable. You remember in one of my recordings, I used this really, really nonsensical example. If we were trying to measure the efficiency of our air conditioner outside during the summer months, and we put a thermometer in the front yard and we put a thermometer in the backyard, and we use those two. I mean, those two are collecting pretty much the same data. And so you're not really sure exactly how independent variable 1 and independent variable 2, how they relate to each other, although that correlation, it's got to be close to 1. But then if you have, other independent variables like, number of clouds in the sky, et cetera, you can't really distinguish between and among the impacts of those slope coefficients. And what it does is it inflates those standard errors, which increases the type 2. Now let's just finish up here with a conversation on R squared. Remember in the last recording, I said something to you like, hey, some really, really good models can have a low R squared, and some really, really bad models can have a high R squared. But what we know is that when you have multicollinearity between or among some or several of the independent variables, you're going to have a high R squared. That's just the way it works out. But what you can do is you can say something like, look at a high R squared, and you're thinking, oh my gosh, this is a great model. But then you look at the F test and the F test and the T test, they say something like, oh, they're not the same result, right? Remember, the F test is kind of a test of the overall effectiveness of the model. So you can have a model that's pretty effective, but what is going to happen is that some of your independent coefficients are also going to be statistically significant. But think about this. Suppose that you have an F test that says, hey, this is a great model, and then you look at your individual t-stats and none of them are significant. Well, this is probably because of multicollinearity. And then there are a couple of different ways you can do this. I mean, the best thing to do is to go out to your front yard and pick up the thermometer and throw it away. You don't need that second one. But you can also do this stepwise regression in which you say, okay, let's go ahead and let's take the air conditioner, whatever that dependent variable was, and the thermometer in the backyard and clouds in the sky. Let's do that model. And then what we can do is we can add that third one, that second thermometer in the front yard, and then we could add a third thermometer in the side yard, and then we can reverse our way back. We can just go ahead and eliminate some of those and try to figure out which ones are important and which ones are not. The interesting thing is that when you're performing these kinds of analyses, clearly thermometer in the front yard, thermometer in the backyard, those have high correlations. But it's not as obvious with financial data. Think about my example with dividend yields. So what's going to be a really good, economically sound, independent variable? Changes in operating cash flow. That sounds like a reasonable one to me. But then what was my other independent variable? Quality of the executive leadership team. Well, there's probably correlation between highly skilled executives and changes in operating cash flow. That might not be quite as obvious. So you need to perform these extra tests. All right, so that takes us through these learning outcome statements. Know what a correctly specified model looks like, and then know the consequences of model misspecification, and then know about heteroscedasticity, serial correlation, and multicollinearity. So I think this was a good one. We're going to revisit this in these next and future modules. So thanks for watching, and have a great day, and good luck studying.